Did you know that on Mercury you could actually outrun the sunrise? If you walked at a brisk pace toward the horizon, the sun would seem to hang motionless in the sky, or even move backward, a phenomenon called retrograde motion. This isn't science fiction, it's just a consequence of the planet's really bizarre orbital mechanics, a kind of cosmic dance between its slow rotation and its super-swift journey around the sun. This strange reality is just the opening note in the grand symphony of the inner solar system. These first few worlds forged in the hottest part of the solar nebula are not just, balls of rock. They're characters in a cosmic drama, each with a story of fire, ice, pressure, and time. Imagine the solar system as a vast celestial neighborhood. The sun is the blazing hearth at its center, a nuclear furnace that, dictates the rules for everyone. The planets closest to this fire are the terrestrial worlds, Mercury, Venus, Earth, and Mars. Our first stop is the most enigmatic of the inner worlds, Mercury. It's a planet of superlatives, a world of extremes. It's the smallest planet, the fastest planet, and the closest to the sun. From its surface, our star would appear more than 3 times larger and 7 times brighter than it does from Earth. Beneath its cratered, moon-like surface lies a heart of pure iron. Mercury's core is enormous, making up an astonishing 60% of the planet's entire mass, compared to Earth's core, which is only about 17%. The leading theory is a story of ancient cosmic violence. A catastrophic impact with another massive planetesimal could have stripped away most of its original crust and mantle, leaving behind the dense metal-rich core we see today. Let's talk about time on Mercury. A single solar day on Mercury, the time from one sunrise to the next, lasts a staggering 176 Earth days. That's 2 full Mercurian years. During the long, sun-drenched day, surface temperatures can soar to a blistering 430 degrees Celsius, hot enough to melt tin and lead. But during the equally long night, temperatures plummet to a cryogenic minus 180 degrees Celsius. Our ship of the imagination now departs from the scorched plains of Mercury and sets a course for the second planet from the sun, Venus. From a distance it looks serene, a brilliant, featureless jewel in the morning or evening sky. It is often called Earth's twin. It's nearly the same size, has a similar mass and density, and was formed in the same neighborhood of the solar system. But this twin is not our friend. To pierce its veil of clouds is to enter a realm that, honestly, Dante himself could have scarcely imagined. The result of this runaway greenhouse effect is a surface temperature that is, in a word, hellish. The average temperature on Venus is a staggering 462 degrees Celsius. The surface of Venus is a volcanic wasteland, covered in vast plains of basaltic rock, punctuated by thousands of volcanoes. Mapping this hidden world was one of the great triumphs of the space age, achieved by NASA's Magellan spacecraft. While NASA's Magellan mission gave us our most comprehensive map of Venus, the first to actually touch the surface were the Soviets. Their Venera program was an audacious campaign to conquer the hellish world next door. The breakthrough came on December 15, 1970. The Venera 7 lander successfully touched down, becoming the first spacecraft to soft land on another planet and transmit data back to Earth. A few years later, Venera 9 and 10 sent back the first images from the surface, revealing a flat, rocky landscape under a dim orange sky. The pinnacle came with Venera 13 in 1982. It survived for 127 minutes and transmitted the first color images, showing flat, angular rocks and orange-brown soil under that eerie ochre sky. It even drilled a sample of the surface rock, finding it to be a type of basalt similar to that found on Earth's ocean floors. After the inferno of Venus, we set our course for home. The third rock from the sun, Earth. From a distance it is a swirl of blue, white, green and brown, a living world. It occupies a special place, a Goldilocks zone where conditions are not too hot and not too cold but just right for liquid water to exist on its surface. Our planet's size is also just right, large enough to retain a substantial atmosphere and a molten core that generates a protective magnetic field. Unlike the stagnant lid crusts of Mercury and Venus, Earth's surface is dynamic and ever-changing. The crust is broken into a mosaic of tectonic plates that are constantly in motion. When charged particles get trapped in the magnetic field, they create the spectacular light shows we call the aurora borealis and aurora australis. Of course, the most unique feature of Earth's surface is life itself. From the deepest ocean vents to the highest mountain peaks, life has colonized nearly every inch of our planet. Our journey through the inner solar system brings us back to where we started, but with a new perspective. We have seen a scorched, iron-hearted world that dances to a strange cosmic rhythm. We have visited a veiled, hellish twin, a cautionary tale of a paradise lost to a runaway climate catastrophe. And we have returned to our own world, seeing it not as ordinary, but as an extraordinary exception. The missions that took us to these worlds are extensions of our own senses, allowing us to analyze worlds that are beyond our physical reach. And so, we look up at the night sky with new eyes. We see Mercury, a fleeting spark near the twilight horizon, and we know the story of its iron heart and its strange long day. We see Venus, the brilliant evening star, and we know the story of the inferno that hides beneath its acid clouds. And we see our own world, the pale blue dot, as Carl Sagan so eloquently called it, as a fragile oasis in the vastness of space. Our journey through the inner solar system is a humbling one. It reminds us of our cosmic loneliness, but also of our incredible privilege to be alive and aware on this one special world. The quest to explore is a quest to understand, and in understanding other worlds, we ultimately understand ourselves. It is a curious thought. The Sahara Desert, that vast ocean of sand, was not always so. Only a few thousand years ago, a mere blink in geological time, it was a green and vibrant land. Rivers flowed where there is now only dust. Hippos and crocodiles thrived in deep lakes. This remarkable transformation is not a myth. It is a secret whispered by the earth itself, a profound reminder that our world is not static. It is a place of constant, powerful, and sometimes bewildering change. The ground beneath our feet is not a fixed stage but a dynamic actor, forever rewriting its own story through wind, water, ice, and fire. This planet is alive. Imagine the Earth as a magnificent, self-regulating machine. Deep within, its molten iron core acts as a giant furnace generating immense heat. This heat must escape. It rises through the planet's mantle in slow, powerful currents. These currents are the great conveyor belts of our world, the engine of our planet, plate tectonics. This internal engine has a partner, the sun. Our star bathes the planet in energy, but this warmth is not distributed evenly, creating a fundamental imbalance. Nature tries to correct this, setting the atmosphere and oceans in motion. This constant circulation is the genesis of our weather, a breathtakingly complex symphony. The planet has kept a diary written in stone. Every layer of sedimentary rock is a page from this diary, capturing snapshots of forgotten worlds. Geologists can look at a towering cliff face and see a story unfold. Ancient deserts, rising seas, warm oceans teeming with life. One profound story is Snowball Earth. 700 million years ago, geological evidence suggests our planet froze almost entirely, a world encased in ice. The rocks record the air itself. These formations show when early life began pumping oxygen into the atmosphere, creating the breathable air we depend on today. The great ice sheets are Earth's most pristine library. Each year adds a new layer, trapping tiny bubbles of ancient atmosphere, perfect samples preserved for hundreds of thousands of years. By drilling deep and extracting ice cores, we can travel back in time, layer by layer, season by season, a frozen chronicle of our planet's climate. Projects like Epica have been revolutionary, showing that for 800,000 years, atmospheric carbon dioxide fluctuated between 180 and 280 parts per million, moving with ice ages. When temperature records are laid next to greenhouse gas records, the correlation is astonishing, demonstrating the powerful link between greenhouse gases and planetary temperature. Few phenomena are as dramatic as the supercell thunderstorm. This is a meteorological beast, a single, vast, rotating updraft called a mesocyclone, king of thunderstorms. A supercell requires a volatile recipe, abundant moisture from warm water, atmospheric instability, and wind shear that twists the rising air column, setting it spinning like a top. Once formed, the supercell becomes a self-sustaining engine. Its rotation separates updraft from downdraft, allowing it to persist for hours and travel hundreds of miles. These storms are most common in Tornado Alley, where unique geography brings all ingredients together, a perfect breeding ground for atmospheric monsters. If a supercell is focused violence, a hurricane is a sprawling engine of chaos, the largest storms on Earth born over warm tropical oceans where water exceeds 80 degrees Fahrenheit. A hurricane is a giant heat engine. Warm, moist air rises and condenses, releasing tremendous heat, creating a powerful positive feedback loop that intensifies the storm with breathtaking speed. The storm's spiral shape and calm eye result from Earth's rotation. The Coriolis effect deflects inflowing air, creating the iconic spiral and tranquil eye surrounded by the most ferocious winds on the planet. A single mature hurricane releases energy equivalent to 10,000 nuclear bombs, a profound demonstration of Earth's ability to move energy and the vulnerability of those in their path. Our most comprehensive understanding comes from silent sentinels orbiting above, a constellation of Earth-observing satellites acting as planetary guardians, continuously monitoring our world's health. Ghost satellites remain fixed over the equator, providing familiar satellite loops on evening news, tracking clouds and hurricanes in real time with images every 30 seconds. The Jason series measures sea surface height with millimeter precision, revealing ocean hills and valleys caused by currents and identifying warm water pools that rapidly intensify hurricanes. Missions like Aqua, Terra, and Grace provide undeniable global evidence of our changing climate, moving Earth study from local observations to truly global science. Our planet remains deeply mysterious. We know more about Mars than our ocean floors. Deep Earth processes, subsurface life, and precise mantle mechanics are active research areas. Climate feedback loops remain sources of intense study. Clouds cool by reflecting sunlight but warm by trapping heat. Tipping points for ice sheets and rainforests are not yet known. We are now co-authoring Earth's story. Our knowledge has given us profound understanding of the delicate balance making this world habitable and grave responsibility. The journey continues, driven by curiosity. More secrets await revelation, more storms to understand, more mysteries to solve. In seeking to understand our planet, we may better understand ourselves. Let's begin with an object you know intimately. An object of simple, everyday utility, found in kitchens and cafes across the globe. Here's something to chew on. Take a teaspoon. Hold it in your mind's eye. Feel its familiar weight, its smooth, cool surface. It is a tool for measuring sugar, for stirring coffee, for sipping soup. It is mundane, it is normal. Now we are going to use this simple spoon for a thought experiment that will take us to the very edge of reality. We're not going to the pantry for a scoop of sugar. We're going on a journey across thousands of light years, to a cosmic graveyard where the laws of nature are pushed to their absolute breaking limits. Now imagine using our humble teaspoon to scoop up a tiny piece of a neutron star. This isn't just any star. To understand what we've just captured in our spoon, we have to rewind the clock. Imagine a star born with at least 10 times the mass of our own sun. For millions of years it lives a brilliant, furious life, fusing hydrogen into helium, then helium into carbon, and so on, forging heavier and heavier elements in its core. But this process has a fatal endpoint: iron. Unlike the lighter elements, fusing iron doesn't release energy, it consumes it. The star's internal furnace, which has held the crushing weight of its own gravity at bay for eons, suddenly switches off. In less than a second, the star's core, a ball of iron larger than our Earth, collapses in on itself. The outer layers, now unsupported, come crashing down at a quarter of the speed of light, only to rebound off the newly formed ultra-dense core in a cataclysmic explosion we call a supernova. What's left behind in the center of this cosmic violence is the star's ghost, a neutron star. It's one of the densest objects in the known universe. So, what does that teaspoonful of stellar remnant actually weigh? The answer is staggering. That single tiny spoonful of neutron star material would weigh about 6 billion tons. That's not a typo, 6 billion tons. To put that in perspective, that is more than the weight of every single man, woman, and child on Earth combined. It's the mass of all 70,000 of the world's largest aircraft carriers. It's the weight of the entire Great Pyramid of Giza multiplied by 1,000. All of that mass, all of that history, all of that sheer substance fits into a volume smaller than a sugar cube. How is this even possible? Because during the star's collapse, the gravitational pressure is so immense that it overcomes the fundamental forces that keep atoms apart. The vast emptiness within each atom vanishes. Electrons are smashed into protons, creating a substance made almost entirely of neutrons, packed together cheek by jowl. It's a material so dense it's essentially one giant atomic nucleus the size of a city, and its density is just the beginning of its strangeness. When the massive star collapsed, it conserved its angular momentum, just like an ice skater pulling in their arms to spin faster. This means neutron stars can rotate at incredible speeds, some spinning hundreds of times every second. They also inherit the star's magnetic field, concentrating it to a level that is trillions of times stronger than Earth's. This combination of rapid spin and intense magnetism turns many neutron stars into pulsars, cosmic lighthouses that sweep beams of radiation across the galaxy. If one of those beams happens to sweep past Earth, our radio telescopes detect a precise rhythmic pulse, the heartbeat of a dead star. This is the kind of physics that plays out in the cosmic arena every single day, operating on scales that really defy our everyday intuition and bend our minds into new and interesting shapes. The universe is filled with phenomena like this, objects and events so extreme they make our most solid realities seem like fleeting dreams. This mind-bending fact about the teaspoon isn't just a fun piece of trivia to share at a party. It's a key. It's a key that unlocks a fundamental and perhaps unsettling truth about our place in the cosmos. We live our lives governed by what feels normal, by the physics of our immediate environment. Gravity is a gentle force that keeps our feet on the ground. A rock is heavy, but we can lift it. The sky is up, the ground is down. Our entire civilization, our biology, our very consciousness is built upon the foundation of this terrestrial human-scale experience. But the universe doesn't care about our normal. Our normal is the exception, not the rule. The universe operates on a set of rules so extreme, so vast and so powerful that our entire planet is just a tiny, fragile exception. The rule of the universe is crushing gravity that can spaghettify planets. It's searing radiation from gamma-ray bursts that can sterilize entire solar systems from light years away. It's the unfathomable absolute zero cold of empty space. Our comfortable world, with its liquid water, breathable air, and gentle sun, is a tiny protected bubble, shielded by a delicate magnetic field and a whisper-thin atmosphere, floating in an ocean of cosmic energies that could obliterate it in a heartbeat. Think about that teaspoon again. It represents the raw, untamed nature of the cosmos. But here is where the story turns, where this terrifying object becomes something deeply personal. The very same forces that create an object as dense as a neutron star are the same forces that give us life. The Big Bang created hydrogen and helium, but almost every other element was forged in the heart of a star. The carbon that forms the backbone of our DNA, the oxygen we breathe, the nitrogen in our atmosphere, all were cooked up in stellar cores. But the story doesn't end there. Elements heavier than iron, like the gold in our jewelry, the silver in our electronics, the uranium that powers our cities, cannot be made in a normal star's life. They require the unimaginable energy and pressure found only in the most violent cosmic events, the explosion of a supernova, or the collision of two neutron stars. The forces that create that teaspoon of dense matter are the same forces that forge and scatter the precious, heavy elements across the galaxy. The iron in your blood, the calcium in your bones, it was all cooked up in the heart of a star that lived and died long before our sun was even a twinkle in the galaxy's eye. We are, in the most literal and profound sense, stardust. We are the children of cosmic explosions. The universe is not just something out there, it is within us. Every atom in our bodies, aside from the primordial hydrogen, has a stellar birth certificate. So, when we look up at the night sky, we are not just looking at distant twinkling lights. We are looking at the grand, cosmic furnace that created us. We are looking at our own extended family history, written in fire and gravity across billions of light years. It's a humbling and exhilarating thought all at once. It connects us to the grandest story of all. This realization changes everything. It changes the very nature of our questions. We move from asking the simple question, what is the universe, to a much deeper one. What is our relationship to the universe? It reframes our entire existence from being passive observers to active participants. We are not separate from the cosmos, looking in from the outside through a window. We are a part of it, a thinking, feeling, questioning part of it. We are, in a very real sense, the universe's way of becoming aware of itself. And that brings us to the biggest, most tantalizing question of all, a question that has haunted philosophers, scientists, and dreamers for centuries, a question born from this very realization of our cosmic origins. If the ingredients that made us, the carbon, the oxygen, the iron, are scattered everywhere, forged and distributed by billions of supernovae across cosmic history, and if the same physical laws that govern our existence apply everywhere, then is it possible that this miracle of consciousness has happened before? Is anyone else out there looking back at us, asking the same questions? Are we alone? The answer, whatever it may be, is the most profound truth we could ever discover. Either we are a singular, precious miracle in an empty cosmos, the universe's sole voice, or we are just one voice in a grand cosmic chorus. Either way, the story is just beginning. Your left hand and your right hand are perfect mirror images of each other. You can place one on top of the other, but they will never perfectly align. No matter how you twist or turn them, your thumbs will always point in opposite directions. This simple property known as chirality is more than just a biological curiosity. It's a fundamental feature of our universe. The molecules of life, the amino acids and sugars that build our bodies, almost exclusively exist in a left-handed or right-handed form. This isn't a random choice, it's a deep, cosmic preference that scientists are still struggling to explain. What if our universe itself has a preferred handedness? Imagine our cosmos as a single massive entity with its own set of rules and properties. The weak nuclear force behaves differently depending on the spin of a particle, violating parity conservation. It's as if the universe has a secret handshake. Imagine you are standing in front of a perfectly still lake. Your reflection gazes back at you, identical in every detail, yet fundamentally reversed. This is the core concept of the mirror universe applied to the entire cosmos. It's a parallel reality that is a perfect spatial reflection of our own. Particles have a property called spin, like a tiny spinning top that can be either left-handed or right-handed. In our universe, the weak nuclear force overwhelmingly involves left-handed particles. Think of a screw. A standard screw tightens clockwise with a right-handed thread. You could design one with a left-handed thread that tightens counterclockwise. Our universe is like a cosmos built with right-handed screws. What if you not only reflect the universe in a mirror, but also swap all particles with their antimatter counterparts? This combined operation is called CP symmetry. Our universe's imperfections might be perfectly cancelled out by its cosmic twin. At the very beginning of time, just moments after the Big Bang, the universe was a searingly hot soup of energy. This energy should have produced matter and its strange counterpart, antimatter, in exactly equal amounts. For every electron, there should have been a positron. When a particle of matter meets its antimatter twin, they annihilate each other in a brilliant flash of energy, converting their mass back into pure light. If matter and antimatter were created in equal measure, they should have annihilated each other completely, leaving behind a universe filled with nothing but light. Yet, here we are. The planets, the stars, the galaxies, and you, all of this is made of matter. For roughly every billion pairs of matter and antimatter particles that destroyed each other, just one single matter particle survived. This tiny remnant is what formed everything we see today. What if the matter and antimatter were somehow separated? Some theories propose that our universe ended up with all the matter, while its mirror twin became the repository for all the antimatter. Our universe's apparent surplus of matter isn't a surplus at all. It's just one side of a cosmic coin. At the smallest, most fundamental scales of reality, space and time are not smooth and continuous. They dissolve into a chaotic, bubbling sea of possibility known as the quantum foam. Tiny fluctuations in energy can spontaneously create pairs of virtual particles that pop in and out of existence in fractions of a second. The many worlds interpretation suggests that every time a quantum measurement is made, the universe splits. Every possible outcome becomes a reality in its own separate, parallel universe. Imagine you're at a crossroads and can turn either left or right. According to many worlds, the moment you make a choice, the universe splits. In one universe, you turn left. In another, a copy of you turns right. Perhaps the Big Bang itself was a singular, massive quantum event that created not just one universe, but two, locked in a symmetrical embrace. They would exist on different branes of reality, separated by a dimension we cannot perceive, yet potentially able to influence each other through gravity or exotic forces. The amino acids that make up all proteins in life on Earth are, with very rare exceptions, left-handed. The sugars, like the ribose in our DNA, are almost exclusively right-handed. This universal preference is known as homochirality, and it's a complete mystery. Why should life choose one hand over the other? In 1997, scientists analyzing the Murchison meteorite found an excess of certain left-handed amino acids. This suggested that the bias for left-handed building blocks of life might be cosmic in origin. Perhaps circularly polarized light from neutron stars or supernovae preferentially destroyed right-handed molecules in the interstellar dust clouds where our solar system formed. In a mirror universe, life would be constructed from right-handed amino acids and left-handed sugars. Such life forms would be visually identical to us, but their biochemistry would be our mirror image. If you were to meet your mirror twin, you could not share a meal. The food from their universe would be indigestible or even toxic to you. If a mirror universe does exist, how could we possibly detect it? This other universe isn't just on the other side of the galaxy, it's in another dimension entirely. Unlike other fundamental forces, gravity is incredibly weak and might be able to leak between dimensions or branes. Physicists at Oak Ridge National Laboratory fire a beam of slow-moving neutrons at an impenetrable wall, looking for a bizarre outcome, a neutron that vanishes from our universe, passes through the wall by crossing into the mirror universe, and reappears on the other side. This theory suggests that particles might oscillate between our world and the mirror world under the right conditions, particularly in the presence of strong magnetic fields. Perhaps the most direct evidence could come from the Large Hadron Collider. Physicists smash protons together at nearly the speed of light to see what exotic particles emerge from the wreckage. If mirror particles were created in a collision, they would escape unseen, but they would carry away energy and momentum, providing a tantalizing whisper from the other side. In the desolate, frozen landscape of Antarctica, a NASA-sponsored experiment called ANITA has been scanning the heavens for ultra-high-energy cosmic neutrinos. It consists of a massive balloon carrying radio antennas high into the stratosphere, detecting faint radio pulses when neutrinos from deep space smash into atoms in the Antarctic ice. ANITA has detected something utterly baffling. Radio signals that don't seem to be coming from space above but rather bursting up out of the ice from below. High-energy neutrinos should be absorbed by the Earth. They shouldn't be able to pass through thousands of kilometers of rock and ice to emerge from the other side. A group of physicists proposed that these anomalous events could be evidence of a CPT-symmetric universe where not only are charge and parity flipped, but the arrow of time itself runs backward. A particle from this time-reversed universe would appear to us as traveling backward in our time, precisely what ANITA observed. It's incredibly speculative, but it remains a genuine, unexplained observation. The idea of parallel universes was built upon the shoulders of giants. Andrei Sakharov was one of the first to propose that matter-antimatter asymmetry could be explained by processes that violated CP symmetry. Hugh Everett III's many worlds interpretation was initially dismissed but later championed by physicists like Bryce DeWitt, fundamentally changing the conversation about parallel realities. Chien-Shiung Wu conducted the famous Wu experiment in 1956, proving that the universe can tell the difference between left and right. This discovery was the first empirical crack in the mirror of cosmic symmetry. Modern physicists like Leah Broussard are pushing these ideas from theory into testable experiments, representing the frontier of physics exploration. The journey to understand the possibility of a mirror universe takes us to the absolute limits of human knowledge, forcing us to confront the deepest mysteries of our existence. The mirror universe offers a solution that is as elegant as it is profound. Perhaps our universe is not the whole picture, but one half of a perfectly balanced whole. This transformation would be as significant as Copernicus realizing Earth wasn't the center of the universe, or Hubble discovering our galaxy is just one of billions. Of course, we must remain grounded. The mirror universe is still highly speculative, and science progresses through rigorous testing and falsifying hypotheses. Yet its power lies not just in potential truth, but in the questions it forces us to ask, and the creative experiments it inspires, pushing the boundaries of technology and theory. As we peer into the cosmic-looking glass, we may only see our own reflection for now, but the possibility that the universe has a hidden twin makes the quest for knowledge the greatest adventure of all.